Hi, welcome back. We are going to start with another new subtopic again, 2.3 Hess's Law. First, we need to know what is the definition of the Hess's Law. And then before we apply the Hess's Law, normally we're going to check whether we can use the formula to do calculation or no. If the formula cannot be used, then only we will apply the Hess law either using the algebraic method or energy cycle method, or based on what the requirement of the question. Then next, we are going to use the energy cycle method to illustrate the dissolution process. And where actually this dissolution process always will involve the enthalpy of hydration, enthalpy of solution, and also lattice energy. We can use formula to solve the question if the question asks us to determine the enthalpy of reaction or enthalpy of changes, at where generally the symbol is delta H. However, you do keep in mind that the formula that we use is this, where we have to alert that basically we need to use the enthalpy of the formation. Okay, if we want to determine the enthalpy of a reaction, we have to make sure the value of enthalpy of formation is given. Let's look at one example here. The thermite reaction involves aluminium and iron 3 oxide with the given equation. The reaction is highly exothermic. So here give us the hints that the reaction after we do the calculation, the value supposedly will be in negative value. And the liquid iron form is used to weld the metals, calculate the heat release. So again, the question gives us the heat release, and then they need us to give in kilojoule per mole of aluminium. However, when we look at the chemical equation here is 2 mole of aluminium. So later, after we get the answer, we need to divide by 2, as we learned in the first video for the thermochemistry. We know that the change of the enthalpy will be different based on the different stoichiometry. So now, we want to check whether we can use formula or no. So if you still remember, the enthalpy change is equal to enthalpy change of formation for the product. P is the product minus the enthalpy change of the formation of the reactant. So when we check the information given over here, this is enthalpy of formation, and this one also formation. Means that for this question, we can apply the formula in this question. So what are the product in this question now here? The first one is the aluminium oxide. So we check the formation of aluminium oxide given is negative 1669.8, and then we have 2 mole of iron liquid. So based on here, we also can check that there is the iron liquid, but this one is kilojoule per mole. Here showing us 2 mole, so means that we have to plus 2 times 6, 12.4, and then minus, there is no more product, so now we need to minus the sum of the formation. Okay, sorry, I missed out the symbol of the sum of the formation of the reactant. So in here, when we check here, there is no information about aluminium solid, because this aluminium is occur naturally. So if occur naturally, that means there is no heat involved. So when there is no heat involved, so the delta H will equal to 0 kilojoule per mole. So that's means in this case, we can ignore the aluminium, and then we continue with the iron 3 oxide, which given in here is negative 822.2. So when we press the calculator, we supposedly will get negative 822.8 kilojoule. But because of the question here need us to do in kilojoule per mole, so that's why we have to make it an enthalpy of the reaction for the aluminium. So we are going to divide by 2, so negative 822.8 kilojoule we divide by 2 more. Why is 2 more? Because over here there is 2 more of aluminium, so that's why the unit will become negative 411.4 kilojoule per mole. Now let's continue with the tutorial question. So based on that, we notice that question 11 is apply the formula that we discussed in the previous slide. Okay, so again, when we look at the question asks us to determine the enthalpy change for the above reaction, for this reaction, and then the data given over here, all these are the enthalpy of the formation. So enthalpy of formation is over here. So again, we are able to use the formula. So we can write down the formula first. Enthalpy change always equal to the sum of the enthalpy of formation of product minus the sum of the formation of reactant. So again, if you are the one who write down the formula, make sure the P write it full product and then R is the reactant. Okay, so then we now look at here, we have 2 more of ethanol. So over here is 2 more of ethanol. So we will use 2 times negative 277.8 and then combine with, total up with the carbon dioxide, another product which also involve 2 more. So we'll 2 times negative 394. Okay, after we settle for the product, then we are going to minus the enthalpy of the reactant, which is the glucose, which is negative 1260. So there is no others reactants, so that is with minus 1 only lah. So after we press the calculator, we will get a negative 83.6 kilojoule. Okay, now let's look at tutorial question number 9. The heat of combustion of benzene, so this one is combustion, is negative 3267.4 kilojoule per mole. Heat of vaporization for the C6H6 and also H2O. So and then the question again also asks us to calculate the enthalpy change. So when we look at here, the enthalpy given in the question is combustion and vaporization, which is different from formation. Therefore, for this question, we are not going to use formula. Okay, so if look at here, I already write down here is algebraic method. So we will continue to get the idea of the algebraic method soon. Okay, so if the enthalpy of formation of each species is not given, means that we cannot apply the formula. In the previous slide, we already mentioned. So we are going to apply the Hess law. Okay, so before we can apply the Hess law, we need to know what is the meaning of the Hess's law first. So according to the Hess's law, they mentioned that the total enthalpy change for a reaction is same whether the reaction is occur in one step or in a series of steps. So the enthalpy change depends only on the nature of the reactant and product and is independent on the route taken. So now we look at the question diagram here. We have A, we consider this A is the starting point. Okay, and then or we depart from A. Then our destination is the B. So here we have two road to goes to B. One is directly from A, we can directly to B. Another row is we need to start from the A to C and then C to B. Okay, so just now we have mentioned that it is independence on the row. Okay, so and then first row we have one step only. Okay, the blue color one, we only have one step. Okay, for the blue color one. However, for the red color one, we involve two steps. So no matter it is one step or two step, the enthalpy change is supposedly to be same. So simple to say, the enthalpy change for H1 will equal to enthalpy change of 2 plus enthalpy change of 3. Okay, this even though we're using different row, but at the end we still reach at the point B. Okay, only one is using one step. Okay, and then another one have a transition station. So even though it's like that, but the energy that used for both rows are the same. So this is the idea of the Hess's law. When we apply the Hess's law to calculate the enthalpy change, there are two methods. One is algebraic method, and then another one we know as energy cycle method. So let's check with the first method, which is algebraic method. The heat of combustion for the benzene given is negative 3267.4 kilojoule per mole, and then we have heat of vaporization for benzene and water, which is positive 33.6 kilojoule and also 44 kilojoule per mole. Then we need to do the calculate the enthalpy change. So before we can continue, when the question gives us the name of the type of enthalpy and also the value, means that we're going to need to write out the thermochemical equation. So again, just reminder, that's why it is very important for us to know the definition of the enthalpy, because we will apply the definition by writing out the thermochemical equation. So here we need to write the heat of combustion and also heat of vaporization. So the first thermochemical equation that we're going to write is the heat of combustion of benzene. So based on what we learned in the previous video, heat of combustion is heat released when 1 mole of substance, so this time the substance is liquid, burn in excess oxygen. Okay, so when burn in excess oxygen, the product will be carbon dioxide gas and also H2O. Okay, so before we can continue, we have to make sure this equation is balanced. So we need 6 mole of carbon dioxide gas. Then here we will have 3 mole of water, because 3 times 2 equal to 6. So basically here we have 3 oxygen from the H2O and 12 oxygen from the carbon dioxide. So total is 15 oxygen. So here we will going to use 15 over 2 oxygen gas. So given here the enthalpy is the negative 3267.4. Okay, next we are going to continue with the heat of vaporization. So from the word vaporization, even though this heat of vaporization is not in the type of enthalpy that we learned before, but then we know that vaporization, the meaning of vaporization means that the change of the physical state of a substance is from liquid to gas. So now we have a C6H6 vaporized. So we'll put C6H6 benzene when vaporized. So the chemical composition does not change, still maintained as C6H6, but the physical state already changed from liquid to gas. So the enthalpy given in the question here is positive 33.6. Okay, so next one is the enthalpy of the vaporization for the H2O. So when H2O liquid, same case, vaporize, it will become H2O gas. And then the enthalpy given there is positive 44.0. So that means step number 1 is we need to write the Step 1, we need to write thermochemical equation. So again, that is why the definition of enthalpy is important. Okay, after we write the thermochemical equation, we will label this thermo equation as 1, 2, and 3. Then again, don't forget we need to determine the enthalpy change for the reaction, which is referred to this chemical equation. Okay, so we check the first substance here is the benzene in the gas phases. So we have to check in the among these three equations, which equation consists of benzene and then in the gaseous phase. So then it is very obvious that we notice that benzene of gaseous phase is in the third chemical equation, thermochemical equation, yes. So in the reaction that we want to calculate, the benzene gas is as the reactant. But in the thermochemical equation here, the benzene gas is in the product. So means that they are at the different position. They are at the different position. One is reactants and then one is at the product side. So what have to do with the thermochemical equation 3? We need to reverse equation 3. So once we reverse the equation 3, means that the benzene gas will be as the reactants and then the benzene liquid will become the product. Because of we reverse the equation, so the delta H need to change the sign, become negative 33.6 kilojoule because initially is positive. So when the position of reactant and the product is reversed, is switch, so we have to switch the sign to negative sign. Okay, next one, we're going to have oxygen gas in the equation. So then we also notice that oxygen gas is found in the first thermochemical equation. Oxygen gas is at the reactant. In the first thermochemical equation, oxygen also as the reactant. The coefficient is 15/2. This one also 15/2. Means that it is exactly the same. So we can maintain equation, thermal equation 2. So if we maintain thermal equation 2, then we just rewrite again this thermochemical equation. 1 mole of liquid benzene react with 15/2 mole of oxygen gas, which will produce 6 mole of carbon dioxide and 3 mole of H2O. Sorry, it's out. You have to include all the physical state. And then the enthalpy change, because you didn't change the position of the reactant and the product, you didn't switch, and then the coefficient also remain the same. So the enthalpy also will be, the value or the magnitude of the enthalpy also will be maintained the same. Release 3267.4 kilojoule. So the next one, we are going to look at the carbon dioxide. So carbon dioxide gases also notice is in the first thermochemical equation. Here is gas, here also gas, and then here is 6 mole, this one also 6 mole. At the equation, first thermal equation is product. In the chemical reaction that we want to determine, also in the product. So means that already in the question. So we no need to do anything because it's already here. So I will circle this one because this is what we want. And then we proceed to the next one, which is the H2O. So H2O here is H2O gas. So we can notice that the H2O gas is over here at the second thermochemical equation. So here is product, here also product. So means that we are going to maintain the third equation. However, here it is 3 mole of water, H2O gas, but here is 1 mole only. So we need 3 more. So that's why the third thermochemical equation need to times 3. So once we times 3, we will get 3 mole of H2O liquid and then produce 3 mole of H2O gas. Since now the the coefficient is different, here is 3, here also 3, so means that we need to multiply this enthalpy with 3. Okay, but at the same time we don't need to change the sign because the position of the H2O liquid is both, gas are both at the product. So for this one, the delta H will equal to 3 times positive 44 kilojoule. Then now, how we going to solve this question? So we repeat again here. So after we decide, so basically from here we need to decide we maintain or reverse the equation. And then we need to multiply or we reverse. So this one is step 2. So after that, we're going to check, okay? So based on this equation. So I erase the things that I write down over here so that you will not confuse. Okay, so now according to this question, this is chemical reaction that we need to determine. We need 1 mole of benzene gas. So this is 1 mole of benzene gas. We circle first. And then we need 15/2 mole of oxygen gas as the reactant, 15/2 mole of oxygen gas at the reactant. And then we need 6 mole of carbon dioxide gas, 6 mole of carbon dioxide as the product, 6 mole of carbon dioxide gas as the product. And then next one, we need 3 mole of H2O gas as the product, 3 mole of H2O gas at the product. So those needed in the chemical equation that we want to calculate the enthalpy change is already circled. Therefore, those are not circled, we need to make sure they can cancel out each other. So for example, now we can see over here, 1 mole of benzene liquid, and then this one is benzene liquid. They are at the different side, so it can be cancel out each other. So the other one is H2O liquid, 3 mole of H2O liquid, and this one also 3 mole of H2O liquid, at where we also can be cancel out. So after we cancel out, end up, these are the remaining product and the reactants that are in the reaction. 1 mole of benzene gas with 15/2 mole of oxygen gas and 6 mole of carbon dioxide gas plus 3 mole of H2O gas. Okay, so which is exactly similar with what the question asks us to calculate. So if this happens, so end up later when we want to do the calculation, we just need to total up all these. Okay, we just need to total up all these enthalpy change. Okay, after we press the calculator, you will get the answer. The delta H is equal to negative 3169.0 kilojoule per mole. So if you want to specific, here you can see that this is enthalpy change of combustion for benzene gas, because we burn 1 mole of benzene in excess oxygen, 1 mole of benzene in excess oxygen. So we can say this is enthalpy combustion of benzene gas.